¿no? Genau. Mhm. والله أنا جربت فاضل الميتنج أي دي جاي من الموبايل ما كنتش واخد. بس هي مش تطلع هنا عشان خاطر الفول سكرين. جرب من تليفونك تأكد هي بتطلع على المفروض تلغى. هقول لك حاجة، في ميتنج أي دي كده. لا مش هتطلع، دوس على يور أي. لا ستوب شيرنج وهتلاقيها. شغالة. تمام. بص، دوس على الخضرا اللي فوق دي، على القصة. كام؟ 8 4 1 7 0 1 4 1 7 0 1 5 5 ماشي. شير كده معرفش. هو شير سكرين. معمول معمول شير سكرين، معمول شير أصلا. كمان مش طالع. كمان مش طالع. لا كمان انت مش باين عندي. اه طيب. اه
So, hello everyone, let's start. Sorry for the delay. I am Mohammad Rahatul Islam Udoy. I am a third year PhD student in the ECS department of UPK. So, in this class, we will not be discussing any theory, maybe, but we'll do some hands on works. At first, we will do some circuit simulation and then we will do some hardware experiments. So, I have brought some equipment for all of you. When we will start the hardware experiment, we will just distribute it to you. I have that in the class actually. So let's start. So first thing is what is simulation? Uh, do you have any idea of what is simulation? Anyone? What comes first into your mind when you hear about simulation? Test. Yeah, exactly. Yeah, it's a test, and it's actually simulation. I mean, it's trying to mimic the real world actually. Okay, some or not the entire real world, but some part of the real world. Okay, so let me tell you an example. Suppose, how do you think the pilots of the aeroplanes are trained? Do you know? Yeah, that's the kind of simulation. At first they do not actually fly the planes. Before that, they have to actually go through the simulation. I mean, they have created an environment of the airplane, and then just they are using it to train the pilots actually. So, having said that, can you give me another example that you may have used in your life uh, as a simulation? Anything?
In one of my classes, we use live virtual machines to kind of like enact a sandbox environment.
That's an example. There is maybe another funny example. There should be you actually are well known of maybe actually. That's a funny example actually. What could be it? Especially the teenagers.
Computer games?
Yeah, exactly. The computer games are actually simulations. Okay, that are actually those are actually simulation of some part of the real world. You just simulate it in the computer. So that's actually a simulation. And even the police, but polices are trained with simulation. I mean, there are softwares, simulator softwares. A few months ago, I went to the Knoxville council meeting, and they are trained with simulators actually. They are instead of training them in the real scenario, at first they are trained with simulations where different kind of scenarios takes place, and then they actually go through those scenarios and become trained actually. So simulation is very important part in every aspect of the real world. And in our case, we have to simulate our circuits before making it in real life actually, because sometimes the circuits are very much expensive, and we do not know how will it behave in the real world. So at first we have to simulate the circuit, and then we will go to the real world and make the circuit, because actually chip we are talking about, the chip inside your computers and mobiles are actually the fabrication of those chips actually takes months to actually fabricate them or to print them out. So if you need to test something, you have to do it in the simulation. So so we have to simulate the circuit as well. In our case, we have different kinds of simulation or circuit simulator. So let's move to a simulator tool. At first, we will simulate in a software called Tinkercad. Okay, this is an actually online software. You can just create an account and log in. There and use this software to design circuits. What is the difference? There are actually many circuit simulators in the market. Why we are choosing this? Because the components you will be taking in the software, it will exactly look like the real world components. Like we actually make the circuits in a breadboard for prototyping. So in other circuit simulator, you may not have breadboard. You have to just abstractly connect the circuits. But in this case, you can use the real world, real physical breadboard, battery, etc. And the components in this software exactly look like the real one. And we have the breadboard. I will talk about the breadboard, battery, and the resistor. And this is the real breadboard actually. This is the picture of the real breadboard. We will, I have that. You will use this breadboard to create or make circuits. So at first, this is the breadboard, and as you can see, there is no bread here actually. So this is the breadboard where we actually make connections. So you know that we have to connect the different resistors and voltage sources. So to connect them, we use this breadboard. Let me go to the. I have to point it. Let me turn on the pointer. Okay, so this is the breadboard. You can see there are a lot of holes here. So you have to insert your components, circuit components, into these holes. As you can see, there is a resistor, and resistor has two terminals, right? These are the two terminals, and you have to insert these terminals to these holes of the breadboard actually. So how the breadboards are connected, I mean how the pins of these breadboards are connected or holes are connected. As you can see that, okay, this is the connectivity actually. So as you can see, the upper two layers, I mean upper two rows of holes are connected horizontally. They are actually connected. if you connect one pin right here, this and another pin right here, these two pins will automatically be connected actually. Okay, so I have to tell you that if you, all of these lines of pins, look at the top line actually, the top row of the holes, these all are connected actually. So if you connect something right here and connect something right here, they will be connected inside the breadboard. The connections are made inside the breadboard. If you don't open it, but if you open the back side of the breadboard, you will see the connections. But don't open it, because if you open, connections may break actually. So yeah, I mean, at the bottom layer of the breadboard, I mean, in the opposite side of the this view, actually there are connections. So these are the connections. Actually, the upper two lines are connected horizontally, and the lowest two lines are also connected horizontally. And what about the middle two rows actually? So they, as you can see, it is written already in the slide. It's connected vertically. Okay, so if you make a connection right here, and you make a connection right here, they will be all automatically connected because they are connected inside the breadboard. Okay, so we will use this breadboard to connect circuits. We'll make the circuits on this breadboard. And you know this is a battery. Many of you already know this. This is 9-volt battery. We will use 9-volt battery. That's why I have chosen the picture of a 9-volt battery. But there, you know that there are batteries of different volt ratings. I mean, 1.5 volt double A batteries are maybe 1.5 volt, and then other batteries 5 volt. So we have in our stock we have 9 volt. That's why I have put a picture of 9-volt battery. And let's talk about meter. So I'm talking about the components that we will use today. So that's why there are other components, but we will use these components. So this is a multimeter. The name suggests multimeter, that the name itself suggests that it's a multi-purpose meter, right? Because we can measure current, we can measure voltage. We have to measure voltage, we have voltmeter. There is another meter which is called voltmeter, and to measure current we have ammeter. Okay, and to measure resistance there is a ohm meter. But all of these are combined inside a meter. Then it is called multimeter. I mean, the name actually suggests what it does. It is actually a multi-purpose meter where we can measure voltage, current, resistance. But unfortunately, I have the meter today that has no capability of measuring current, but it can measure voltage and resistance, etc. Okay, so that. Yeah, let me skip. Let me go to another slide before going to the previous slide. So I will be show you the heading. So and there is a difference between connecting a voltmeter and ammeter. A voltmeter, as I have said, that voltmeter measures voltage and ammeter measures current. Okay, so you measure voltage across a device. Okay, you always measure the voltage across a device. So this is a 9-volt battery, and this is one bulb, maybe one load. You can say one bulb. This is the second bulb. So I need to measure the voltage across the bulb. So I connected them. Look at the voltmeter. Voltmeter has actually 2 terminals. Okay, so we have to connect these 2 terminals across the device. Actually, suppose I want to measure the voltage of this bulb. So I need to connect the voltmeter across this bulb or device. Actually, that's how I will measure the voltage. And for current, as you can see, this ammeter has 2 terminals, and this is connected in series with the circuit, as you can see. And so there is a difference between a voltmeter connection and ammeter connection. Ammeter is connected in series with the circuit actually, and voltmeter is connected in parallel with the device that we want to measure the voltage. Okay, so without maybe talking much, let's move to the real thing. So we will use Tinkercad for this class, which is a software, which is a computer software. So we will simulate the circuit in the software first. Then we will do this. Then we will make the circuit physically actually. So to test this, before this is actually how industries or real world works. At first, they design the circuit in their head, and they simulate the circuit inside any software. Maybe not this software because the industries have different different softwares to simulate their circuits. So this is an example actually. So this is how a real world circuit making works. So at first they design the circuit in their head, and then they simulate the circuit inside any simulator, circuit simulator. And then if that works perfectly in the circuit simulator, then they actually create the circuit physically. Because creating the circuit without any simulation or without any assessment, it will actually the circuit can blow up actually, and it could be very expensive and time consuming actually. So we have to simulate that circuit in a simulator first. So to create an account in Tinkercad, just these are the steps actually. So you have to go to tinkercad.com. Maybe if we can create an account and go to Tinkercad, that will be actually helpful. So could you please create an account in Tinkercad and go to tinkercad.com, and we will select circuit right there. So if anyone needs help, let me know. Have you successfully go to Tinkercad? So after you create the account, the interface will look like this. So in this Tinkercad, actually, you can design many things, including circuits, maybe. So you can also create 3D designs here. We will need that as well, actually, the 3D design of Tinkercad in the next phase, maybe, because there will be a hardware project where we may have to, besides circuit, we may have to use a 3D printer, which we have in our lab, in the main cow building. So we will use that Tinkercad, we will use that 3D printer. But to print something in 3D, you need 3D models, right? You need to generate 3D models of something. So we will design 3D models right here also, in the Tinkercad. But I'm not using this feature right now. We will use it later. So let's go to the circuits section. This is the circuits. So let me go to this circuit section, and you may want to create a new circuit here from here, and just select circuits, and this kind of window will open. Okay. So this is you can see a white space here. Here you will design your circuit. Place your components and etc. So at first, to get all the components, you have to select all from this components list actually. So make sure that here all is selected under the components section. Okay. Then at first we will make the circuit on the breadboard. So I'm just typing breadboard. So as you can see that there are various types of breadboard. They differ in sizes. We will use the standard size breadboard. So if you click that, and there will be a breadboard sticking with your mouse, and you have to just place it somewhere with a left click actually. So this is the breadboard. Let me show you a physical breadboard as well. So actually, this is a physical breadboard. So you will use it right today actually. So so that's actually yeah. If you hover your mouse on the holes, it will actually show which pins are connected. So here, as you can see, that I have placed my mouse on a hole and it shows all the connections. I mean, this pin, if you connect something in this pin, and if you connect something in this pin, those two will be shorted actually. I mean, they will be connected. But yeah, in the software, you can see that there are connection where there are connections, but in real world, you will not see actually. So you have to memorize this, that which pins are actually shorted. I have just written that on the slide for your reference, and you can check which pins are connected before actually making the circuit. So okay, so we have taken the breadboard, and then we suppose we want to simulate a circuit, and for that we will need a battery. Let's start with the power source. So let me search in this search box with maybe 9-volt battery. You have to search 9-volt battery. So this is the 9-volt battery. Place it outside the breadboard. Okay. And if you want to rotate this, you do not like the orientation of this component. Okay. If you do not like the orientation of this component, you can rotate it by just pressing R from the keyboard. Okay. Just press R, it will rotate automatically. I mean, it will rotate and place it somewhere here. Okay. So as you can see, there are two terminals of a battery. I'm just zooming in. As you can see that the red is the positive one and the black is the negative one. So if let me connect it, I am connecting this positive terminal to this hole of this breadboard. Okay, just click and just press click here, left click will end the connection. So this 9-volt battery is connected here. So I have a question for you. What should be the voltage of this pin? Do you know? Let me show you. Let me tell you again. This positive terminal of the 9-volt battery is connected to this pin. Okay. So the second row of this breadboard. So what will be the voltage at this point? At this breadpoint? Right. Exactly. Yeah, because they are connected. Yeah, I have already told you that these two lines are horizontally connected. So if you connect something here, it will be automatically connected here. So this whole pin, the whole row here will represent now 9-volt connection. Okay. So if you need 9-volt in the circuit, you can take any pin from this row and connect it here. It will get 9-volt. The circuit, all of these pins will give you 9-volt. Okay, and similarly, I will connect this negative pin to this row, and now this is the negative pin. I mean, in the DC circuit, although it is represented as negative, but we reference it as 0 or ground. Okay, we have. I think you know that there is a ground in the circuit, which is a reference point. That's actually an imaginary reference point actually. So this is what is ground in a circuit. Actually, the lowest voltage node in the circuit is called a ground. So let's not worry about it. Before that, what I am trying to actually doing actually. So let me before that, let me open another. Maybe open a page to draw something. At first, we need to clarify our target. So I'm drawing the circuit, what I want to implement in the breadboard. So let me draw the circuit. I want to make this circuit. Suppose this is a 9-volt power voltage source, and this is a resistance. You are already familiar with resistance, and I want to make this circuit. Simply this. Suppose this this resistance is 1K. What is 1K? Do you know? What does K means? Yeah. Yeah, 1000. Yeah. So in the circuit, K in the circuit or not in the circuit, anywhere in the world actually, K means kilo or I means 1000. Okay. So 1K means 1000. And in a similar way, do you know what does 1 M means? Not 100,000, it's 1 million. We can say 1 million. In the circuit world, we tell it 1 mega. Okay, mega. You heard about, you're familiar with megabyte, kilobyte. That's this mega actually. So 1 mega means 10 to the power 6. Okay, and 1 kilo means 10 to the power 3. 1K means 10 to the power 3. I mean, this is 1K, 10 to the power 3 means 1000 ohm, and 1 mega means 10 to the power 6. That is, there is a list, I think, in the previous slides. So we will often use kilo, mega, giga, this kind of things. 1 mega. I think these three will do. We do not need, there is another one with M, with lowercase m. This is called milli. Okay. So milli means 10 to the power minus 3. We do not need this right here, maybe, but just to differentiate between lowercase m and uppercase m, I'm just telling you that 1 mega means 10 to the power 6. So when I tell you 1 mega ohm, it means that 10 to the power 6 ohm. The unit of resistance is ohm, right? This is the sign of ohm. And when I tell you 1 mega ohm, it means 10 to the power 6 ohm. And when I tell you 1 kilo ohm, it means 10 to the power 3 ohm. And there is another one. Oh, I'm writing it sequentially. So 1 kilo is 10 to the power 3, 1 mega is 10 to the power 6, and there is other one which is 1 giga. What should be, according to the sequence, what should 1 giga equal to?
9.
10 to the power 9, exactly. So 1 kilo 10 to the power 3, 1 mega 10 to the power 6, 1 giga equal to 10 to the power 9. Okay. So and it actually goes on, but we do not need them actually. So it's I think enough. There are other big numbers actually. So we will frequently need these 3 numbers. So just keep in your memory. So let's go back to the circuit. Okay, so we want to make this circuit where there is a 9-volt voltage source, 1 kilo ohm resistance. Other resistance maybe it's 2 kilo ohm. So we want to measure. We want to make this circuit in the breadboard. Okay, so with that in mind, I have connected the voltage source 9 volt. Let me keep them side by side so that we can compare. I think that looks good. Okay, so we have connected the voltage source. Then what do we need? We need 2 resistors. Okay, so first come to this 1 kilo ohm resistor. Just in the component list, just search for the resistor. So this is the symbol of resistor. In real life, the resistor looks like this actually. So that's why this is given. So this is the resistor. I would like to rotate it. So I am pressing R from the keyboard. So I want to connect it in the horizontal direction. So I'm just placing it right here. Okay, in a random place in this. So the rule is, the thumb rule is actually, so you have to connect the voltage sources in these two upper lines and these two lower lines. The voltage sources, you should connect the voltage sources in these two lines and the other circuit components in between these two rows actually. Okay, so I have placed the resistor in this section, in this area. So, and if you select the resistance, you will see the resistance value right here, which is right now 1 kilo ohm. What we need is 1 kilo ohm. So it's already selected 1 kilo ohm. So I'm not changing anything. And I think you know the resistance color code, right? So you can just check this, is it 1K or not? Okay, so I'm just now trusting the software. This is 1 kilo ohm, and then let's take another resistor because we have two resistors inside our circuit. So let's take another resistor, and in a similar way, I will just rotate it. Rotate it and placed it somewhere. I have not connected them yet, so I need to connect. I have placed all the components because, as you can see in the circuit, I have 9-volt voltage source. I have resistance, one resistance, and second resistance. So I have placed two resistances or resistors and one 9-volt source. Now I need to connect them. Okay. So as you can see, the 9 positive. Let me change the color. So as you can see, that 9-volt, the positive terminal of the 9-volt is connected to one terminal of a resistor. Okay, so this is I have told you that this when I have connected this positive terminal of the voltage source right here, so every point here is the positive terminal of 9-volt. So I can connect it from here because it is the shortest distance because the wire will be less. So I am just connecting this point. You have to just click left on the mouse, and there will be a wire sticking with your mouse. So this is one terminal of the resistor. So if I connect this right here, I'm not directly connecting this wire to the left terminal of the resistor. Okay, what I'm doing, I am just connecting this hole. And I have already told you that these rows are connected vertically. Okay, so if I connect this wire in this pin and the left terminal of this resistor is already connected. Okay, internally they are connected because I have already told you that these are vertically connected internally. So if I connect this with this pin, it will be connected to the left terminal of the resistor. Okay, then yeah, I have connected the positive terminal of the voltage source to the left terminal of one resistor. Then what do we need to do? That we have to connect the other terminal. This is a resistor. I have connected one terminal already. We have another terminal of this resistor, which will be connected to the left terminal of the second resistor. Okay, so the right terminal of the first resistor will be connected to the second left terminal of the second resistor. I mean, these two will be connected. So let's do that. So this is the right terminal of the first resistor. I'm just taking a connection from here. Just I'm clicking left, and then I need to connect it to the left terminal of the second resistor. That's how I have connected. So in this case, the same thing is applicable as well, because I have told you that these all holes here are connected vertically. So if I connect right here, the left terminal of this second resistor will be automatically connected to this pin actually. So we have connected this portion, and this we have connected the one terminal of the second resistor. The other terminal will be connected to what? The negative terminal of the voltage source, right? So the second resistor's right terminal will be connected to the negative terminal of the voltage source. So this is the right terminal of the second resistor. So I'm taking a connection from here, and then where is the negative connection? Negative connection, or I mean the negative terminal of the voltage source, right in this line. Because as you can see that I have connected the negative terminal of this voltage source in this line, and the whole line is connected here internally. So if I connect a pin here, this will be automatically connected to this wire. Okay, so this is automatically, this line is automatically connected. So I think the circuit is complete here. All the connections have been made. So we have just made this circuit in the breadboard. And what will we do now? So let's do some task here. What does we suppose we need to measure the voltage across this first resistor. Okay, so what should we do? So we need to, as I have told you in the slide, that to measure voltage across a device, you need to connect a meter across the device. I mean, let's go back to the slide. So this is the voltmeter connection. I want to measure voltage. Okay, so I will be connecting one terminal of the voltage source in one side of the device, and the other terminal of the voltage source to the other side of the device, because I want to measure the voltage of this device. So let's connect a voltmeter in the Tinkercad. So I am searching for a multimeter. Here I am a meter will do. So here is the multimeter. If you search meter or multimeter, you will find this device actually. So where you can measure the voltage, and as you can see, there are three knobs in this device. One is marked with A, the other one is B, the other one is R. So A means ammeter. You can measure current with this setting, and V means you can measure voltage, and R means you can measure resistance. So we want to measure voltage. Okay. So before measuring the voltage, let me calculate the voltage with our hand calculation. Okay. I think you are familiar with voltage divider rule, right? Because that was taught in the previous classes maybe. So let me draw something to describe. Okay, so what is voltage divider rule? So we have 9 volt here, and we have a resistance of, suppose I am marking it with R1 1K and R2 with 1K. So this 9 volt, remember one thing, that voltage is
R2 was 2K.
Oh, sorry. Thank you for reminding. Okay, so keep in mind one thing, that voltage is divided in series. These resistors are in series, right, with the voltage source. These are R1 and R2 is in series. So this voltage source will be divided between these resistances. Okay, so this division is very simple. This suppose you have $500. So one friend will get maybe let's do the math of ratios. Okay, so suppose this should be divided between 2 friends in this ratio 3:4. Okay, so friend 1 will get, I mean, this $500 will be divided between 2 friends, and the 2 friends and friend. So you're in this ratio actually. So the question is, how much the friend one, I mean the first person will get. How will you do the calculation? So I mean the question is, let me clarify the question. So you have to divide $500 between two friends in this ratio, 3:4. Okay, so how much the friend one will get? The math is I think simple, because they have to do what? 500 into 3 divided by 3 plus 4, right? Isn't it the math? So actually this, so if you calculate this, you will get the friend one's share actually. And for the friend two, what you have to do? 500 into 4, this 4 is coming from here, and you need to add this. So what is the rule? So you have to take the whole amount, the total amount, then you have to multiply it with the ratio of this second friend. I mean the second friend will get 4. So I am putting 4 here, and under this I have to put the sum of these ratios actually. So that's how you will get the share of friend 1 and friend 2. Voltage divider rule actually acts in the same fashion, exactly the same fashion. The formula is the same. So you have to take the whole, I mean the total voltage, what is being shared, and then in the numerator we have to put, I suppose I am measuring the voltage of R1, so I am naming it VR1. Okay, so right now I'm measuring the voltage of R1. So I'm taking the whole, I mean the total voltage, and then I'm putting the resistance value of R1, because I'm measuring the resistance of R1. So I'm putting the value of R1, which is 1K, and then I have to add all the resistances in series. So this is how many resistances are there? 1K plus 2K. If I had another one, I had to, if I had another one R3, I need to add that as well in then I mean in this summation actually. Okay, so because I have 2 resistances, that's why I have 2 terms in this denominator, and let's calculate that. So 9 into 1K divided by 3K, right? Then this 3K will be cancelled out, and we will have 3 volt. So we should get 3 volt across this resistor. Okay, 3 volt. It's our hand calculation. So we know that hand calculation is boring. That's why we'll be using softwares, because this is a simple circuit. Hand calculation is easy here, but when the circuit becomes complex, then the hand calculation will be very tedious actually. So that's why that's one reason that we use circuit simulator, because this kind of hand calculation is not possible for every circuit. So I mean the complex circuits, it will be tedious. So, but to trust the simulator, we have to test the simulator maybe. So to trust the simulator, we are setting a test case here. So in this hand calculation, we are getting 3 volt across this resistance. So let's see, or let's observe that is it true in the simulator as well. Okay, so let's go to the circuit in the Tinkercad. Now let's connect this multimeter or voltmeter. Right now it's in the multimeter is in voltmeter setting. I mean it will measure voltage, because I have selected, I mean it's automatically selected in voltmeter setting. So let's connect the positive terminal of okay, let me describe the connection in here as well. So I will be connecting here voltmeter right here. So how should I connect it? As I have told you that voltmeter should be connected across the device. So I have this voltmeter, and I have to connect one terminal right here and the other terminal right here. But the voltmeter has 2 terminals, which the one of is the first one is positive terminal, and the negative. The second one is negative terminal. So we should put the positive terminal in the high voltage side, because as you can see that the 9 volt is in the left side of this R1 resistor. So I have to connect the positive terminal of the voltage source to the high voltage side of the resistance. Okay, and there is another negative terminal. There is other terminal which is a negative terminal which we should connect to the other terminal of the resistance. So let me connect that. So this is the positive terminal, which is the red one. So I have to connect it to the left side of the resistance. Okay, remember that. So which one is the left side of the resistance? This one. So I'm connecting one pin of this column, because I have already told you these are connect. These all pins are connected vertically. So I'm connecting right here. So it will be already connected to the left terminal of the resistor. Okay, and then what about the right terminal of the resistor? What about the negative terminal of the voltmeter? This will be connected to the right side of the resistor. Okay, so this is the right side of the resistor. I have to connect it anywhere in this line. So these all are short. These all are connected. So the voltmeter connection is done. Okay, and to clarify which wire is which. You can just change the color of the wire maybe. So to change the color of the wire, you have to select the wire, and then you have to go right here. This is the wire color. You can change it to red, or any color. And I am changing this black one to this green one to black, the negative terminal of the voltmeter. Now you can see the connection. It's actually crossed, so no problem at all for this. So I think our voltmeter connection is done. Now we have to start the simulation. Okay, so there is a start simulation button in the top right corner. So you have to just press it. And one thing, this is 4.5 volt, because the second resistance is also 1K. Let me just and another thing, if you want, I have actually put the resistance, second resistance. I have not changed the value of the second resistance. It's 1K. That's why it's showing 4.5 volt. Actually, in our circuit, in our calculation, this second resistor was 2K. I have not changed it to 2K. So I am going to change the circuit. So before changing the circuit, please stop the simulation, because otherwise it will not work. So to change any element of the circuit, you have to stop the simulation first. Okay. And let me change the resistance value, because as you can see that when I select the resistance, it will show the resistance value, which is 1K. I need to change it to 2K. Okay. So let me change it to 2K. Just you have to, instead of 1, you have to just write 2 in from your keyboard. Then just left click anywhere in the white space. It will be changed to 2K. So right now it's 2K. The first one is 1K and the second one is 2K. Now let's start the simulation again. So as you can see, this is 3 volt, which was also we have already calculated that with our hand calculation, that I could across the resistor 1, it should be 3 volt. So actually, yeah, this is very very. And if it's 3 volt, let me ask you one question. What should be the, without any calculation, can you tell me that what should be the voltage across the resistance 2 or R2? Anyone?
6.
Exactly 6, because the 9 volt is divided here. Okay, so now from 9 volt you already getting 3 volt across the R1. So the other 6 volt will be dropped here. So without any calculation, I can tell that it's 6 volt, because the summation should be 9 volt, because this 9 volt is divided between this R1 and R2. So we can also calculate that. Suppose we do not know that this is 9 volt, sorry, 6 volt. Let us do the calculation and check if we are right actually. So suppose we are measuring the voltage across the resistance R2. So the formula is the whole, the total voltage that is being divided into the resistance of R2, because I am measuring the resistance, I'm measuring the voltage across R2. So we have to put R2 in the numerator. 2K and in the denominator we have to put the summation of all the resistances, which is 1k plus 2k. So if we calculate this, so 9 volt into 2k divided by 3k, so k's are cancelled out, and if we just and 3 cross 2 is equal to 6 volt. Yeah, with this formula of the volt, and this is called voltage divided rule. With the formula, we are also getting that the voltage across R2 is 6 volt. Okay, so let's measure that in the circuit or in the Tinkercad, in the simulator. So let me change the connection. Before changing the connection, let me stop the simulation first, and then you need to change the connection. Maybe we can take another voltmeter because we have no limitation here. We can take multiple equipments or elements, circuit elements here. Let's take another meter, which is the same voltmeter. And how should I connect? Yeah, so positive terminal in the left side of the resistor. So yeah, let me clear up things. Let me see here. So this was our resistance 2, which was 2k. So we are connecting another voltmeter here. So to connect another voltmeter, suppose this is a voltmeter, and the voltmeter has a positive terminal and a negative terminal. So positive terminal should be connected to this terminal. I mean the left side of the resistance 2. I mean R2, and the second the negative terminal of the voltmeter should be connected to the right terminal of the resistance 2. So let's connect that. So this is the positive terminal, and I should connect this with the left terminal of the second resistor. This is the left terminal of the second resistor. I'm connecting it here again. These all are connected, and then let's change the colors. It's black right now, and the next color should be black. Okay, so the negative terminal here, which is the black one, should be connected to the right terminal of the second resistor, which is here. So the second voltmeter is connected already, and now let's again in our hand calculation we got that the voltage should be across the second resistor should be 6 volts. So let's start the simulation. Yeah, that's true actually. So across the second resistor we are getting 6 volt, and across the first resistor we are getting 3 volt, and this is a 9 volt battery. So it's actually a 9 volt is divided in such a way that the first one gets 3 volt and the other one gets 6 volt, and if you sum up these two you will get 9 volt. Okay, but in the real world this is actually an ideal case. Okay, in the real world you may not get exact 3 volt or exact 6 volt. It might be 2.99 or if you sum this up or if you add this, you may not get exactly 9 volt because there are some drops in the breadboard. Actually, let me draw it to better understand. So this was our circuit, and this is resistance 1, this is resistance 2, R1, this is R2. So this was 1k and this was 2k, 9 volt. So these are the connections, but in these connections this is wire or something. We will be connecting with wires, and there are connections inside the breadboard as well. So those connections are called conductors, right? But the conductors has resistances as well. Okay, so where there is resistance, there will be a drop. I mean, there will be a drop in the voltage. Maybe I mean, they will consume the voltage. Actually, what are this R1 and R2 doing? Actually, they are consuming the voltages. So R1 is consuming 3 volt and R2 is consuming 6 volt. But if there is a hidden resistance right here, which is maybe very low, which can be 10 ohm. These are 1000 ohm and 2000 ohm. Okay, and if there is a hidden resistance, we are not calculating in the we are not taking them we are not considering them in the hand calculation, but they are there actually. Okay, so in the breadboard there may be hidden resistances of wires which could be very much low value, but this resistance will also consume some voltages, maybe very few. I mean 0.1 volt or 0.01 volt like this. This is not crucial right now, but in the chip design, the wire, I mean this interconnect, these are called interconnecting chips. Okay, the connections. I mean you have to connect the resistance 1 to 9 volt. Okay, so you have to connect it through something. I mean through conductor, but the conductor has resistances as well. So there can be drop. But in this case, this is actually 9 volt is too high for electronic circuit. But in the electronic circuit, I mean in the microelectronic circuits, these drops are crucial because the interconnects has also some resistance, and there is research going on how to minimize those interconnect resistances. Okay, but in our case, it's okay because we are not worried if some voltage drop are there in the circuit. But yeah, when you are designing industrial level circuit, you have to calculate each and every resistances. So in this circuit, there can be hidden resistances in the interconnects or wires, but we are not considering them right here. And as you can see that Tinkercad is also not considering those resistances because it is giving me exact hand calculation voltages actually. So okay, we have done this in the Tinkercad or simulation, and we'll do the exact same thing in the breadboard physically. So let's do some hardware experiments. Okay. So I am putting the equipments here. So we have plenty of breadboards, so each of you can take.
Yes, on slide number 10, there is a question. You like to do it before we start?
Slide number 10. Okay.
Next slide.
Oh, okay. Yeah, I will describe it later actually after the.
So this is not the same concept.
Yeah, exactly. This is the same concept.
So I think it would be good practice for us to just do it ourselves because you showed us how to do it. So just to see that.
Yeah, this is actually homework. You can do it and show me in the next week maybe.
I just want to make sure they got it.
Oh,
Before we go to the hardware.
Oh, got it. So yeah, I think I can describe it later maybe.
No, I want us to do it and you check that it's right or
okay.
wrong.
Oh,
So
but
just say like
but this is hand calculation. We do not have bulb right here.
No. In the Tinkercad web.
Oh, okay, Tinkercad. Okay, got it. So before doing hardware experiments, we can do it here. Okay.
Like if I understand the topic, so I should be able to do it, and if not, then you guys can help us. Makes sense.
Yeah.
So I have a lot of help
That
from
makes
us.
sense. So okay,
Just
so,
create this circuit in Tinkercad.
okay. So let me describe this circuit maybe. This is the same thing as just I have described. It is a 9 volt battery source. Voltage source, and there is a. I should go there. And let me. Okay. So this is the problem here. This is the same circuit. This is 9 volt voltage source, and this is instead of resistance, I have just used a practical equipment, which is the bulb. Inside bulb there is resistance. Okay, this kind of resistance. In each devices actually, in each equipment there is a resistance. So suppose we do not know the resistance of this bulb, and we have a voltmeter suppose. And there is a resistance right here in series with the bulb, which is the value of this resistance is 10 ohm. So we have to calculate. We don't know the resistance of the bulb, so we have to calculate the resistance of the bulb using Tinkercad. You can use Tinkercad and you can measure anything, and you have to. No, you cannot measure anything. So there is a resistance meter inside Tinkercad, which you can use to measure
We
the.
measured that resistance with our hand calculation, with the theories that are
Yeah, I think we have to do both hand calculation and the software. We need actually both.
Do you have all the information to calculate that resistance? Right?
Exactly. Yeah. So let me. You have to create this circuit in the. I'm giving you a small hint. You have to create this circuit in the Tinkercad and measure the voltage across this bulb. And using that voltage, you can calculate the resistance of this bulb using the voltage divider rule. So actually, this is the hit actually. So yeah, so they will make this right here. Will they make this? Or if you understand, you can do it in the home actually, or whatever you like actually. What should we
Because,
say?
to be honest, like we're like 4 or 5 students, so many teachers. So I just wanted to like take some time to understand how we do connect the calculation that we learned previous classes with this experience. That we see that we got it, or before we jump into it. Like it should not take that long time, right?
Yeah, I think so. So yeah, so everyone to make this circuit. That should be simple.
Yeah, and you can ask help because
So yeah, so make this circuit in
we
the
just go create new again.
Yeah. So if you need any help, let me know. Do you need any help? So do you need any help?
How do you start a new file?
Okay, sorry.
How do you start a new file? Like,
Okay, let me show maybe for
Yeah.
everyone. Doing that. Right? Okay, so let me go back. So if you want to create a new circuit, this is one of your circuits, suppose, and then you need to go back and create a new circuit. Just click on this logo, maybe. Just click on this Tinkercad logo in the top left corner. Then you will come to the home page and just make sure that this tab is selected to circuits, and then just press create from the top right corner, and then so you have to select circuits from it, and you will get a new sheet of circuit.
Can you go back to the slide that has the circuits? I'm sorry. Get the similar the breadboard, the same one, right? Same
Yeah, exactly the same one.
When you connect the terminal, the bulb has a terminal 1 and terminal 2. So I go to terminal 1 to the positive side of the bulb.
That's for. Yeah, I think this anything will do. Yeah.
Doesn't matter.
No, because there's no positive and negative terminal, so that so doesn't
First
matter.
I can do here and this one bottom here. It's fine.
Yeah, it's but the second terminal should be connected to the resistance. So yeah, the second terminal should not be connected to the negative.
It's not connected, right?
Yeah.
Second terminal to the resistance.
Exactly.
And the resistance.
The other terminal of the resistor should be connected to the negative.
This is fine. That this will just connect to the power.
Yeah.
And this will go to the
Yeah.
negative here. Is that correct?
Yeah, exactly.
And this one I change it to 10.
Yeah.
Yes, which is that. Like starts finishes.
Yeah, but so to yeah, it's doing fine actually. It's going on. The simulation is going on. So you have to measure the voltage across the bulb. So you need to take the meter.
Thank you.
Yeah, the second terminal.
Two.
Here, pick the move the bulb because if you connect them in this line, they are shorted actually. So you are basically shorting. I mean, the connecting the two terminals of the bulb, but as you can see in the side, the two terminals are not connected actually. So the first terminal of the bulb is connected to the 9-volt battery source. The other terminal is connected to the resistor. But you do not need to connect the two terminals of the bulb. So if you connect them right here, then the two terminals of the bulb will be connected. So yeah. Exactly. Yeah.
Right.
So we can connect the
Positive terminal should go remember that. The positive terminal should go to
make for the terminal of the bulb.
yeah, the positive terminal to the left. Negative terminal.
Yeah.
After we connect the positive.
Negative terminal is connected to.
You see it better there.
So that's why we actually use different colors. Yeah, so select the wire and just change.
But this one also be red since it's positive.
You can, but yeah,
That doesn't
that-
really matter.
that- yeah, because that is confusing. That's why I
Yeah.
color. Yeah, then that was
Mhm.
correct. Yeah. Okay, so 7.26 volt, and you have to do the hand calculation, right? So
Would it matter which way you flip the resistance?
no, because the resistance terminals, there is no positive and negative terminals for the resistor. The two terminals are, if you can, if you change the polarity, it doesn't matter. Okay. No, yeah, it's just we need just this voltage 7.26 volt.
Why it's not 10?
It should not be 10 because if you add this up, it should be 9 volt.
Combination. Okay, got it. This is fine then.
Yeah.
Right. So you have to do the hand in.
Yes. So actually, this was the circuit where the same 9 volt voltage source, and this is a bulb. The resistance of this bulb, we don't know the resistance of this bulb, but we do know the resistance of this second resistor, which is 10 ohm. So if you make this circuit in Tinkercad and measure the voltage across this bulb, so you have to connect the positive terminal of this voltmeter to the left terminal of the bulb, and the right terminal of the bulb should be connected to the negative terminal of the voltmeter. So you should get 7.26 volts or something like that. Okay, so from this voltage, how can I calculate the resistance of this thing? This is the question. This is our R1, right? So according to voltage divider rule, what should be the voltage across the R1? The formula is VR1 is equal to total voltage into the resistance of the resistance R1 and the total resistance in the series connection. Okay, so what we have got here, we have already measured the voltage VR1, which is 7.26 volt. Okay, so I'm just filling up the equation. So 9, and we do not know the resistance R1, right? So I'm putting R1 here, and again in the denominator we do not know R1, but we do know R2. Okay, so the value of R2 is 10 ohm. Okay, this is an equation, and if you just calculate the equation and change the sign, you will get the resistance R1 value, right? So that's how you will. That's how you can calculate the resistance of an unknown device actually. Okay, I think there are other questions in that homework as well. You can just do some brainstorm and answer those questions. I hope they will be enjoyable. This is the main theme, and you can complete this in your home. And let's start the experiment. So what will we do in the experiment? We'll do the exact same thing actually. So in our hardware experiment, we will take a voltage source which is a 9-volt battery, and we will have one resistance R1 and the second resistance R2 in series, the same circuit. Okay, exactly same circuit. And at first, we know that this is 9-volt voltage source, but we do not trust this is 9-volt voltage source. We will measure the, suppose before making the circuit, just measure the voltage of the battery, maybe, because we have meters, we can measure the voltage of the battery. So check that if the battery is 9 volt or not, because if it's a old battery, it is possible that the voltage is not 9 volt, maybe it's 8.5 volt or something. So before starting making the circuit, please measure the voltage of the battery, and also you will be given 2 resistances. So I think in the back there is in the package there are 4 resistances. Take any 2. Okay, take any two and put it as R1 and R2. But before putting this inside the breadboard, please measure the resistances, because you can measure the resistances in the similar fashion. I mean, just the resistance will have two terminals. Just connect one terminal, the two terminals of the resistance with the meter, and you will get the reading of the resistance value. Maybe it will be better if you get this equipment and see it yourselves actually. So yeah, we have. I'm just making a set. Maybe that will be easier. Thank you. So this is actually one set. We'll try and match it. Yeah, that's the sample. For the other. Oh, not. Just. Do it again? Yeah.
So
Out and record the whole room again. Get us. Can change. You don't want to share this with them. Anybody?
Awesome. Thank you so much.
Thank you. Well, thanks. It's like,
Oh yes.
I don't know. Okay, I think it's better.
Oh, let's just keep it here. Yeah.
Okay.
No problem. Thanks.
to any.
Thank you. So I hope you have got the equipment or circuit components. So let's first take out the multimeter from the box, because we will start by measuring the voltage of the voltage source or battery we have been given. So we need this multimeter itself and these two wires actually. We don't need the other wire. So we don't need that one. We need these ones actually. The thicker ones. I mean. So these are two terminals of the multimeter actually. So we need to at first connect this to the multimeter. So this is simple. There is a cap in one side of this terminal. So we have to remove the cap first. Okay. So these caps are attached. So we have to remove the caps. And then we need to connect this to the multimeter. Okay. So this red goes to the red. As you can see, there are two holes in the multimeter. One is colored red and the other one is black. So you have to just match the color and put it there. Okay.
These are jump wires. I don't know. No, so you have like a voltage source and voltage. These are
Yeah.
This is just
I think it should also say say.
It's the window, it's the wall.
So we have to connect this battery because this is not going to be connected to the breadboard. So we have to connect it to the battery.
That's just on the sometimes we'll have resistance to they're just complicated. It's production. So, let's say you're
So okay, now we need to measure the voltages of this. Oh yeah, yes, she has already started. You have to turn it on. Right now it's off instead. So you need to measure the voltage. It's the voltage.
Picture.
Depends on where you put this. No, up here. Right.
Anywhere. This the bottom row.
Sorry. Yeah, it's slightly over, right? So you can take a note that what is your voltage value. You can take a note because the hand calculation will be changed. How much is it? Okay, so I think this is not perfect. 9 over 9.
There's none.
But it's over 9.
You see these little electrode needs extension levels.
Yeah, so according to that, our hand calculation will also be changed.
Over. What's that too? It smells like this. It's red, negative, and spots. Just this.
Oh, say you wish.
Have you taken the note for the for this source? Okay, so keep a note because it will be used in the calculation. Then we need to calculate the we need to measure the resistance. Yeah, so in this batch, so you have also so I just have the meter. So we can include resistance and measure the resistance and also keep note.
Are they different?
Yeah, they are different. There are different phrases.
Yeah. So once you put one thing in here, it'll fire it up. So if you put a jumper in here.
What is this?
It's a jumper.
To measure the resistance, you can use the breadboard. Okay.
It's also connected.
That's what these are. You choose whatever. Say if you got one.
That's how I can make it do that. These are.
Now, not this one because it will not enter this time of work. Yes.
So eventually. Have you ever seen an alligator?
Yes.
It's not clear. This is how they water. Usually this will say this is our. This is where it compares.
So actually, it was not in auto settings. That's why it's. If you play that, well, I mean, so then you press select. Then
Yeah, then also
the default setting is you need to select the range because it doesn't know which range is
This
in
one you see the red.
because it's in kilowatt, but it doesn't. That's right. So that's what is the default setting because by default it does not know. So you have to make sure that
It's gonna put down there and then whatever.
then just then you can do check yourself. The unit is above right now. Okay.
Measure
Yeah.
the resistance.
Okay. So to measure the resistance, if you use the breadboard, it will be easier. The breadboard is
you want.
One of the resistance, one like
One of the same.
other way. So yeah, make sure that this is in auto mode. If you press the button, this will go to auto. Okay, make sure when you measure all time you should be using auto. So now
Building an RC car.
make sure that it is
That motor.
you have to give some time. And the unit is it's kilo. So you have to also write this. If this is your R1, right? Take a note that this is R1. This is something.
About that. Anywhere. Oh, okay. That's what happened. So God.
These same line. As other one.
Changing.
Sometimes on the it's not the button.
Okay.
So like we're gonna show how to measure like constant.
See my fingers keeping them together. These are from.
Right, actually, did you press anything?
Oh,
there we
okay.
go. There you go. Now it's right.
Touching.
Yes.
Yeah.
It's fantastic.
So you can see that we got 10 or 100, because it's 100 and then you have the chemical, so it can run it. This one should be.
Switch from
And then sometimes you'll see fluctuations just because there's more.
switch from K to M.
It's hard.
It's switch from K to M.
Yeah, it's not much. By default, it goes to omega.
Alright, so
No problem, but you must take the release when anyone just
Good. So your computer. You can select like picture.
What is this?
So,
Yeah, sure. The multiple stuff.
Not sure.
So here.
But you
see this end is gold. Well, isn't actually a number for its color. It's actually a number for its colors. How much your resistor can change that value. So this is this much more.
If I open it, it's gonna.
Say the resistor is 10 kilowatts, right? Plus or minus 10%, right? It may be 9, but when we measure it, it might actually be 9 kilowatts. That's tolerance. Yeah. And then actually, you can on the multimeter, you see where our voltage is, right? This one actually doesn't measure current. This one doesn't have or see a multimeter. In meters, what you have in current. Yeah. What is brown? Yeah. This one actually. Well, that's it. It's just say like the first thing it's kind of just showing you that, but each like it really just look at the column. After these colors goes with one of those. So much of
Yeah, no.
it's the first.
We are just pressing resistance here and
The
other.
is brown.
Okay, so not
So you say something, you find something. Okay, so we're gonna make you'll always just look at something. Listen, it can be a bit inconvenient.
All right, it's brown then.
That's black.
What
You see how you're thinking it's yellow, but that's actually the color. So it's just you see what beige is. Beige here. Green is this one's like blue. So beige here, this is like this is the color that it's so it's not. This one here, this is striped. And you see this here. This is like the gap in between the stripes. That's the resistance, right? Then you have this. You have another.
Very sure.
Roasted. Oh, we look at that. We have our first two are going to be the first two numbers.
Brown, black, and golden.
So if we follow this, we'll have brown and black. And then orange is blue. So that means we're multiplying by so it's 10 times 10. I think it's 10. 10. Oh yeah. So yeah, 10,000. So that would mean this is 10 kilowatts.
Okay, as per me, then it is.
Still.
Is this the voltage?
No, We know this is a 10 kilo ohm resistor, right? The goal tells us that we can have that plus or minus 10%. So see, this is voltage, right? We go over here. This is resistance. Now it doesn't. That's not.
So have you got the resistance values?
Changing. Oh, hold on. What is
Yeah, you have to keep in mind that which one is what. Yeah, so
This one is 5.
okay, got it. This is matching with this color code. The value is well matching.
See, it's like 9.8.
Okay,
The 10K one?
yeah, so
The 10K one.
there is a power effect if the ratio will not be exactly the same because yeah. So
This is how this measure does the.
How much was the word?
Me holding it down against the table, get You can see at the top.
okay,
of
that's
it,
basically
yeah,
okay.
yeah, so let me just multiply that.
P means Q.
Yeah.
So it's 10.
So, yeah, like you see with the other bands, that's how it's $10,000.
Yeah.
That's not exactly $10,000.
So has it been gold?
Yes, they're golden, so I guess they will never.
They are very so
It eventually goes down to 0.
Makes sense. What if you came out of circuit, then we have to go this.
It's actually pretty.
you can do that. Yeah. So you have just pressed the the component, but you have not connected that. Okay.
So
These are
these
the
are
ones. So
You
can use anyone you are. No problem, but it's
Pretty good.
we are all the same.
So we can. Oh. So it's. But you see, we did not.
Not first tax.
It's just. Then you actually see here it has a letter, right? So, you know, you're seeing it just work, but like just a lot of work.
They're in the city.
So like say you see the C circles, you can just follow it. So here's these fiber optic to this voltage, so it's high. You plug the other.
So those.
We short your resistance.
Yeah, so you can move a wire
We
around.
got the same voltage capacity, right? So we have V minus V over that resistance. You're gonna end up with 0.
Okay, so yeah, so if not,
So that's the only thing that you can.
what is the value of this?
If you imagine there's
This way.
I think that was, yeah, so it keeps changing numbers.
Yeah, I use
It's
that.
changing the variance, and then it goes down to 0.
This node is actually connected to.
Measure resistance into in the markets in the resistance.
Yeah, he changed it to.
Small. Yeah. I see.
You have a resistor going across.
Yes.
5.0, right?
Because
Notice that this resistor has a node connected also to the battery. It's the other.
Everything is connected. So
9.04.
it's this one.
You have to take another resistance.
And then now we want to add this arc so we're gonna do anything goes between these two resistors. So how would you do that? So just grab the resistors.
This one.
This stuff is just packaged. This is kind of like the box.
Straightforward.
It's just.
Connect the wire to it.
To measure the resistance, so,
That has like all the. But the aluminum would get ruined at like sand rocks. It's just like transition. So I wouldn't have to redo the whole wood. These ones, they don't have this problem.
This degrees Celsius and degrees Fahrenheit, but I'm not sure.
It's not cheap.
We talked.
Oh, no, I accept you.
We do another one.
Degree Celsius should measure the temperature. NCV should measure. I don't know that. But just leave the borders. Not having any idea what those two.
Bulbs.
No, we need to connect the resistance.
So then we find the voltage across each.
So we.
Positive and negative.
Not for resistors,
Not matter.
resistors, you could take this out, but certain works.
So
Before matter doesn't matter.
Let me
do
show
some hand calculation and check that it matches with the So before that, calculate the voltage across those resistors by doing some hand calculation. It should close the math
Or anything similar to
the resistors for the voltage across
Notice this on the striker. Those are negative signs to show you that that has to be connected to the negative signs which should be honest. Not because it's a capacitor, but because electrolytic capacitors polarity matters. If you put it in the wrong way, it'll pop.
Got it.
Basically, it's not going to really do anything. It's
So
allowed.
for that.
Here, better to put his. I'll really make it his. There does. But you see, it doesn't give us a good reading.
Let's see if we have a picture.
So if we look at this, it's about 2.6 kilograms.
However, so let me clarify the task clearly, maybe. So at first you have to measure the voltage across the battery. So it may not be exactly 9 volt, so it could be anything. And you have to also at first measure the resistance. Suppose this is 5 kilo, it will not be exactly 5 point something or anything 10k. I don't know. You have chosen the resistance randomly, so it can be anything. So you have to measure the resistance. Okay, so suppose it's 5k, it's a random number, and suppose this is 15k. In your case, this will be different actually. So you have to note this number. I mean R1 value, R2 value, and the voltage value. Then before maybe or after whatever. So you have two sides actually. In the left side, you will have theoretical calculations. Okay, and in the right hand side, you will have experimental. I mean, what you will measure using your voltmeter. Okay, so in theory, you have got the voltage value. Maybe it's not 9. It's suppose it's 9.5. So you have to calculate theoretically what should be the voltage across the resistor 1. So you will get that using the voltage divider rule, right? So your total voltage, suppose it's 9.5 volt, it's arbitrary. I mean, it's random. In your case, it could be different. And you have to for measuring the resistance voltage across the R1, you have to put the value of R1. If in your case it could be 5k, it could be 10k, whatever, and then you have to you have to add the resistance 1 and resistance 2. I mean 15k, 5k plus 15k in my case. In your case, these numbers will be different. and you will get a number, right? And in a similar fashion, you will get the resistance value theoretically using this formula, like this 9.5 into then the R1 divided by R1 plus R2. I mean, this is in theory. See, you will get a step-up voltage. So this is in theory. Then you will then or after or before, whatever. Experimentally, you will connect this circuit and measure the voltage across the resistance. You will get direct VR1. It will be some kind of value, and VR2 it will be some kind of value. Then you have to match the theoretical calculation with the experimental calculation. It may not be exactly equal, but it should be near. Actually, I mean, they should closely match. Not exact match, but they should closely match these theoretical numbers, the theoretical voltage across the R1 and experimental voltage across the R1. Okay, so before these things can be done interchangeably. I mean, you can do theory first, then experimental, or you can do experimental then theory, whatever. But let me tell you another thing that there is a precaution. So when you connect the when you connect the circuit, then you cannot measure the resistance. You have to measure the resistance differently. I mean, as a single device. When you connect this resistance inside the circuit, then if you measure the resistance, then it may not give you the correct answer. May not. In some cases, it will give you correct answer. But the best practice is, if you want to measure the resistance using your multimeter, you have to measure it differently. I mean, not in the circuit. Okay, so you can do it after the experiment or before the experiment. You have to measure the resistance value and keep a note and do a theoretical calculation and match with the experimental values. So this is actually the whole task.
It's not good.
It's not working. But you see this auto set, it's setting it up to mega ohms, which is much bigger for the ohms. It's like you're paying those ohms.
So it cannot make it.
This is my first time using multimeters. Usually multimeters don't have a scale and scale.
This year is. I'm so like.
These are bad. Yes. These probably.
The point. Each are some different voltage.
Two people need that.
It's just a tool for him. Yeah.
Space.
Is this program gonna get? It's just competition. It's good for robot.
Should we turn it off?
Turns.
It's good. I don't know what it's fixed.
Mostly just learning. Pretty much they learned a lot of certain concepts. So just like the basic circuit analysis. Maybe that's pretty far. available for ninth graders. Or soon to be ninth graders. Also, there's some height in like with this. I'm not building it, but it'll. Yeah. There's really a lot of these. I just get probably just gonna everybody 17. So she's gone. Well, just go home and sleep. You're a freshman here, but you might really you could do it just like doing things to resist. It's like you're a freshman, you can go back home. No, I'm not good. You're telling the song. I didn't know we could get so. These notes are fun. There's nothing. Yes, it's not close. It's just the close.
Just zero one nine. Battery, right? Battery.
Like
So what is your measure? I measured 9.2. It's supposed to have, I'm gonna get this same next year. So it's, which one's that eight, maybe I'm missing. No, I need, no, it's
So
small.
this row here.
Oh. Can I get it?
Yeah, we can convert it. So they're independent outside.
Yeah, let's see
So
what
if you want
the-
this, you should like this.
she's a lady.
You have to put it in the vertical. So it's other. So you put.
Is yellow, so brown.
You put this resistor inside. You put it from here.
Board.
This
This one is these two.
You can. You'll see your circuit. Yeah, so we put our resistor here.
just a big kind of research center instead of a bunch of guys. Yeah, it's a big national plan.
Sometimes the time when
Yes,
we all
I don't-
buildings and studios.
This is negative.
So that I'm
You might be ready. Oh, yeah, that's yours.
say if we go from this to this point goes to the negative, right?
Yeah.
Here,
It might be.
to this point, it takes us to this point. This point, it takes us to this point. Here, it's in parallel. Like we connected one end of this.
Like a couple branches.
It's going to negative.
Transistors.
Yes, here's
They're combined again. So I don't know if this one is faulty.
I'd say
Long after this, the honest
No.
works, so we can measure it because it's actually basically our auto is
Yeah.
going on.
When it actually into the circuit, then actually may not give you the correct percentage. So you need to pull that up and then whether it can.
We have hospital over there. And then.
Maybe you can some of that. And
There's like a bunch of medical stuff.
yeah,
Something related to medicine. For my options.
Oh.
Thank you. So good to go before you have to think about it.
Also, this was about 100.
Yeah. What was your how
Measure this.
raise
Yeah.
so
Right.
best practice
So that political
so it's best practice it's a very
Oh,
We're either gonna like watch present things.
We could change right after.
If we. I don't remember.
yeah, it's near 10.5, right?
okay.
So,
Let me
you should.
That's not changes.
It's still the same. Nice. I guess now that this, no, this one.
What about this one?
Years since we actually took it.
There we go.
so then actually
So would you say it's so just measure equal or equal as well?
the resistance level was 9.9 kilos.
Oh, yeah, that's 1 year, 1 year, 2, and those don't have to be samples or be anything. And you learning. Or did this, you need to figure out what those numbers are. Like that. It was not. So this same thing, this doesn't make any difference.
These are tied together in rods and these vertical rows, right? And this is tied together. Yeah. This is explained.
You're gonna get out of another big configuration. We still never got like anything.
That's what they call it.
The outside the circuit.
Department was supposed to do that. I don't know if
So you have to remember which one is the R1 and which one is R2. I think that actually. And so this one is your R1 because yeah, you can name it as R1 because it's kind of
They just have to be on the same order.
For these,
bunch of public work.
so beyond putting it on something here. It's R1. Not really that. Not.
maybe first because when the equation comes, that's this whole
Oh, yeah. You're like, what number am I looking for?
Yeah.
It's better.
Well, mine would
It
be,
would be helpful to try and get into resistance at first.
substituting.
But we're substituting in that case our same was 10. That's why we
Oh, rounding.
yeah, but in this case we have that was the difference actually. It's with the 10. That's difference.
You like change.
And it's actually not perfectly 9. In your case it's 9.5.
Oh my goodness. So are these, would you get these two else?
No. It's hard. Yeah, so you have to sound it out.
So whatever you see R2 is gonna it's the negative back, right? Also, it will make it possible.
Yeah, so you have to divide this. Yeah. That makes sense. You know, it's times 0. This I mean,
That's supposed to,
yeah.
yes.
So
The voltage across this race should be this.
also just draw.
Well, I had to- Let's see what happens, see if I get something close to that number. It was fluctuating quite a bit.
Maybe it's not. It's gonna be better.
No. 98.45 right here. So the voltage is actually I want the in the numerator.
The particular part, that's right.
Then you will get the voltage across.
It's no to higher road.
In the numerator, you will get the voltage across.
Yeah, this is the same. This is
The resistance of voltage across the resistance I1 equals to total voltage R1 I1 here because I want to measure the rates voltage across R1. In our case, R1 is this 98.5. So I'm putting 98.5.
So that's the
Voltage across R1.
Okay,
So we use a -1.
so if I was doing for R2,
Yeah, so
then that would go on.
yeah, then 9.9.
I didn't bring that to my.
Okay.
So yeah, so this is your R1, so you will get
like this. No, but also we have this.
Go this.
And then still add the two at the bottom.
This one and this one. Maybe right next to each other, they have to be like those. No, basically, so this is
so
maybe I'm
what is this color? 9.9. Okay.
So that would be the 9%.
Yeah, but where did this 9.9 to come from? This is from
No,
R2, so the voltage will be R2. Yeah, R2 voltage. We write this like a VR.
Yeah, I was like, that's backwards. I knew it as soon as I wrote it. I was like, it'll take me a little bit. So I know that is that. So
Once we
And if one place it will be 9.5.
Can you say admin or?
Yeah.
Which one is your one?
smaller.
Yeah.
Yeah. Okay, I just need more practice.
You don't need to write the whole number.
Oh.
You can put two.
3, okay.
because this full meter will not give you that much.
Well, if you have a 9, would you go ahead
This
and
one
grab
actually
it?
says all about.
Yeah.
But a lot of times you see it has this whole.
Yeah.
Meter on.
So if you measure the voltage actual this R1, this is our R1, you should get it just 8 point something.
Oh, take them out.
Yeah.
For measuring voltage, you don't need to take this out. For measuring the resistance, yes, you need to do that.
But the volts.
Yeah, for the volt you do.
Yeah, we don't measure our voltage. Yeah,
Because the metals are very deep inside this hole, so
actually
if you yeah,
It's in the very.
or just.
yeah, 8.7, which is close.
So close enough, that's one far around it, so yeah, okay, cool.
So these are basic.
And in the similar way, you can extend the
I think it should actually stick. We're making more
It's like that 1.869. Yes.
Yeah.
I mean, this one. This should has been this
This
one.
is not covering it.
Because I'm using this phrase position of 0.86. And he's got 0.86.
Yeah. Okay. Experimenting. Okay.
So, did the results map in your place?
Yeah,
Okay.
I'm still doing doesn't matter. Should we keep it on AC or DC? Should we keep it on AC or DC? Is it not DC?
It should be easy now.
9.24.
Yeah, man. We switch our resistance.
They're the same thing.
That should take that's certain.
Sure, that might be.
Inside the circuit was all this very different.
Because this resistor is.
What was
It being.
What mother in the circuit?
Oh,
It's also.
last year.
Which is all very not to use. I'm not very. From my friends, so. What?
How equally this one is
Bigger, one biggest.
This ended up being the one. So that's.
This one, that is the artwork. This is another.
You couldn't make it.
And then,
7.8.
you know, what's your hair? Yes. Wait, what do you look at? If you're having make decision. The tiny book. Start exploding his world. Okay.
We did. Okay, read this. It's just. It's awesome.
Okay.
So it's hard to. Ideally, we expected that to be like topics. So she would. Just remember though. That's actually really fun.
Exactly. So then that's also.
Yeah, this is actually also just.
Really is kind of what she was. For head conversion, this doesn't matter. So you can see R1.
So you want to do part one?
That's it. Oh, so.
Oh, that's what. Okay, gotcha. There's extra 2 and 3.
Uh,
3.82 or so
3 minutes and
dash. Do you want us to wait?
That's like good. It's just running late.
Yeah, so there would be a break at 12:30.
Oh, okay. Oh, we're close. Okay.
Yeah, please please
Is your portfolio? And then
You notice that's pretty close. That's what
yeah, so it's like
So how's the balance?
6.36.
Are you close?
What's hers is really.
How much?
I got an extra decimal. I got 8.80 and then the right one was 8.82.
That's good.
And then 0.45, 0.45.
That's awesome. But you see, these are actually probably.
So I was only a little bit.
Okay, so your first resident R1, you are getting security fee. How much are you?
Actually 3.8.
I mean, don't write actually, it's experimental. Because yeah, the experimental as well, maybe they
Seriously, sure.
So remember, last time.
Yeah, because like 80 seconds. It's not. There's.
Of these, this is like the. So they share. It's serious.
Classroom.
It's one branch can only have.
It didn't have like
Oh, I hope that's. It's gonna be like, what causes like that? We have to, even if you just have a big business. We wouldn't have any knowledge on technology. Because we don't have any parents, no one who there was. We don't have
Or we won't be serious, it's just keep going. This is also I want.
It's all one.
This is what I always wanted. I just to add this because it's serious.
Okay,
It's
so
really 105. So we. I think we should. I have got to make it wonderful.
That would be expected.
That's the same thing.
So you see on the bottom here, this is 100,000. This is 5. That's this 100,000.
Yeah, so 100 below. Yeah, so in same here.
And up here, that's what I showed. That's what you're looking at. It's 100,000.
Here we cannot.
No, but you have voltage here. Nah, I'm gonna try to put it so you pick the food like this. I think they are stuck in traffic jam, so we'll take care. Okay.
Okay.
It's up to your
So
discretion.
like I don't know how long it will take. Like if it's connected to this, I think it's better to finish it.
I'm
Then
not
after
connected
lunch.
to this actually.
Need the bread. I think
Yeah, then we can take a break.
just wrap up and start.
Yeah.
So you're saying that that's a very good point. So I for this I have to have voltage. R has to be not yours.
Yeah. I think your guys, whenever you use a unit, you want to use it's.
Kilovolt. If I still hold,
Kilovolts is a little, you'll usually see it go down, you'll see like kilovolts. That's not what's, so that's what you
it's current is
basic currents are usually smaller. If your products knowledge is really they call this small signal process. Like the signals are very
so I
or maybe if I remember. I would remember.
found it. Yeah, I think I heard that. Actually, we have with the basic similar, so I cannot use kilo here
Because here we kind of made a shortcut. It's really what we did.
because we crossed it out.
This
Ratio.
is 100,000 over 105,000. Which really what this keeps is 100 times 1,000. What's the about? What about? Yeah. And then what can you do with this? In fact,
Just got this one. Get rid of them.
So this cancels out. And that's really what's happening.
So that didn't matter, but here it does matter. That's
Here,
interesting.
because you have
5 versus 9 over 100,000.
that's a significant
That's significant difference.
Yeah,
So
difference that you can't cancel out. That's very really 105 times the cost that you won't cancel.
we have to divide the answer 5,000 basically.
You could actually just putting a cancel.
Putting zero.
That's usually what I'll do.
This is in my
Zeros, usually which one?
2, 3, 4, 8, 5, 7.
This one's will be reference.
This
You notice.
Okay, so maybe we can take a break and pizza is on the way. So after the break and pizza will start again. Thank you.
So we can do micro just divide by 1,000 again.
So
Yes.
No, you have a different.
Okay, so let's start. So we have actually proven, verified the voltage divider rule. The other name of voltage divider rule is, you can say it's Kirchhoff's voltage law, whatever.
KCL.
Yeah, that was KVL.
KVL.
Yeah, Kirchhoff's. Different people pronounce it differently actually. So I pronounce it as Kirchhoff's. So Kirchhoff's voltage law, KVL, and voltage divider rule are basically the same actually. So we have already verified the KVL or voltage divider rule. Now we'll move to the current. Okay, so this was actually for different the previous circuit, and in this circuit we will actually again in the similar fashion we will verify the Kirchhoff's current law, or other name of this law is you can say current divider rule, or CDR. But current also divided. Current is also divided, but the difference between current dividing and voltage dividing is voltage is divided in series. Okay, so let me draw it to better understand. So suppose there is a voltage source, 9 volt. The voltage will be divided in series. This R1 is connected with R2 in a series connection, as you can see, the series connection. And but if the resistance are connected like this is 9 volt. If they are connected like this is called this is suppose R1, this is R2. If they are connected like this is called parallel connection. Sorry, this is called parallel connection. But in this case, the voltage will not be divided between R1 and R2. Rather, it the 9 both these resistors will get 9 volt, because this is the law actually. So because these resistors are connected between the same terminals, right? So this is one terminal. This is one node or terminal, and this is another terminal. Both two resistors are connected in the same two terminals actually. So that's why the 9 volt will not be divided between them. Actually, the both resistor will get 9 volt. But in case of a current, suppose there is a current coming from the 9 volt voltage source. I'm calling it as I. So it will be divided between this R1 and R2. So some part of the current will go to R1 and some part of the current will go to R2. So I suppose I am naming it as IT. Total current I. It will be divided. Suppose the portion that goes to R1, it is I1, and the portion that goes to R2, I'm naming it as I2. So according to Kirchhoff's current law, so the incoming current and outgoing current will be the same in this node. But for every node it is true. So for this node, IT is the incoming current, right? And the outgoing currents are I1 and I2. So the summation of all the outgoing currents, here these are the outgoing currents, and the summation of all the incoming currents will be equal. So we are not summing anything in the left hand side, because there is only one incoming current. But if there is another incoming current, then we have to add it as well. Suppose we have another current coming from other sources right in this node, which is suppose Y3. Then for this node, the total incoming current would be IT plus I3. Okay, then IT plus I3 would be equal to all the outgoing currents. Okay, so then it would be IT plus I3 equal to I1 plus I2. It is called Kirchhoff's current law. You have already learned this in the previous class maybe. And what is the current divider rule? In the current divider rule, you will know exactly how much current is flowing through R1 and R2. Let me just clear up things. This is R1 and this is R1, sorry for the overheating. This is R1 and this is R2. So this is total current IT, and this IT is divided between I1 and I2. So the current divider rule, or CDR, we call it by CDR. So according to the current divider rule, what should be the I1 value? It's almost same. The formula structure is almost same as the voltage divider rule, but there is a subtle and important difference. So the formula would be I total. Let me write the voltage divider rule side by side so that you can compare. So in the case of voltage divider rule, the resistance wire in series, and there is a total voltage V, suppose VE. So the resistance, so the voltage across the resistance R1 was VR1 is equal to total voltage into, I am measuring the voltage across R1, so I am putting R1 in the numerator, and in the denominator I am just summing all the resistance in the series. Okay, so for the current divider rule, it is almost the same. Here, instead of voltage, it will be the total current, I total, into, let me write the denominator first, the total resistance. In the voltage divider rule, we had total resistance here. In this case as well, we have the summation of the resistances. But here the change comes actually between the current divider rule and voltage divider rule. In the current divider rule, you have to do the opposite. Okay, so for measuring the voltage across R1, you would take R1 in the numerator, right? But in the current, in the case of current, you have to take the opposite. I am measuring the current through R1, so I am going to take the opposite resistance. I mean, it's R2. So when I am measuring the current through R1, I have to take R2 in the numerator. But in the case of voltage divider rule, it was when I am taking R1 voltage, I would take R1 in the numerator. So tell me what should be the current I2. So similar, I total into the same summation R1 plus R2, and then the numerator, what should be in the numerator? R1, right? Because I have to take the opposite, because I am measuring the current through R2, which is I2. So I am taking R1, the opposite one. So this is actually the difference between voltage divider in the formula. Actually, this is the difference between current divider rule and voltage divider rule. So that's how we can measure the current through a device. I mean, I'm measuring the current through R1 and I'm measuring the current through R2. Okay, so that's how CDR current divider rule works. To verify this, we will do the same thing, the simulation first. So for the simulation, I am taking this circuit. At first, we will do the simulation in the Tinkercad. So this is the circuit we have to make in the Tinkercad. So this is 9-volt voltage source, the same battery, and this is the RT resistance. Let me fix the resistance for the simulation. For the simulation, let's keep it 100 ohm, and this R1, let's take it 1 kilo ohm, and this R2 to 5 kilo ohm. Now, our task would be to measure the current I1 and I2. So theoretically, what should be the current? At first, let me do the hand calculation. Then we will verify this using the simulation. So for I1, what should be the current, exact current? It should be I1 is equal to, we do not know the total current yet. So here we have to measure this using a different approach. Suppose in our case, actually, I mean, we have limited sets, limited equipments. And I have already told you that the multimeter you have got, it cannot measure current. Okay. So in real life scenario, if you do engineering, you will face this kind of situation. You will need some a machine, but you will not get that one. Maybe it could be a constraint for different reasons actually. So then the easiest way is to buy it, or you can just measure, or you can use an alternative approach. What does the alternative approach means? In this case, let me describe with this example, with this circuit example. So we don't have ammeter. Okay, so we cannot measure current here, but we can do it. We can do it indirectly. How? Suppose we know the resistance RP, right? 100 ohm. So we have voltmeters, but we do not have multimeter, but we have voltmeter. So if we have voltmeter, we can measure the voltage across RT, right? We can measure the voltage. So from that voltage, I can measure the current. How? And then your answer? Any idea? Any guess? I know the voltage, okay, and I know the resistance. Exactly, yeah, we have Ohm's law. Right? V equals I. I have a simple formula. V equal to I R. So from this formula, we can calculate the current I is equal to, easily calculate the current through a device, I equal to V divided by R. So we will measure the voltage across this resistance RT, that's the V, and we know the resistance RT, which is 100 ohm. We'll plug that in this equation and get the current. So that's how we will indirectly measure the current of the circuit. So yeah, we do not know the total current yet. So let's make the circuit in the Tinkercad and measure the current. Then we will do hand calculation to measure the I1 and I2. Okay, so the I1, the formula is right here, total current IT, we will measure that. And in the numerator, we have R2 divided by R1 plus R2. So we do not know yet what is the IT, and we know the R2. R2 value is 5K. So I'm putting 5, and in the denominator, I am putting the total resistances. I mean, the total resistance where the current is being divided, not all the resistance of the circuit. Okay, because the current is being divided into these two resistance, among these two resistance. So you have to add these two resistances only actually. So you have to add 1K plus 5K. So keep that in mind. So you do not need to add RT here, because this the total current is not being divided in RT here, because the current is not divided in series, because the total current is dividing here. Okay. So and again, you might wonder, I calculate the IT. The same current will flow through this actually. So this is the IT value will be also applicable here. The same IT value will come here actually. Okay, so the current does not drop in the resistance like voltage. So suppose you get current 1 ampere here, you will get the same 1 ampere right here as well. Okay, so current will be divided when there will be two paths. But in this case, from this point, let me name these points: point A and point B. There are no two paths here. This is the single path, right? From A to B, there are no two paths, or there are no branches. So the current will flow flawlessly, and the same current will come from A to B, 1 ampere. Then at this point, the current will get two paths, right? And in these two paths, the current will be divided. You can imagine the current as a water flow in a river. Okay, so from A to B, the water will not be divided because there are no branches, right? But in this point, there are two branches. Now the current will be divided into two branches. So that's why the same current 1 ampere, maybe the 1 ampere is coming to B, and then it will be divided between the two branches. So, and how they are divided, this is the formula actually. So how much this R1 will get, this is the formula, and how much the R2 will get. So this is the formula. I2 is equal to, according to the current divider rule, the new, I'm measuring current through R2, and I should take the opposite, as I have told you that this is different from the voltage divider rule. I have to take the opposite resistance and the sum, and we will get the IT from the simulation, and R1 is again 1K, and R1 is 1K plus 5K. So that's how we will get the current in R1 and R2. So now our task will be to create this circuit in the Tinkercad. Okay, so maybe let's start making this in Tinkercad.
For the IT, should we suppose, because it's 0.09, should I put to 1 or?
No, I'm just taking, it's a random number. This is not the actual value. I'm just.
RT is 100 ohm, right?
Yeah, RT, the resistance values are correct. The voltage also correct. It's 9 volt. RT is 100 ohm, and you have to put R1 1K and R2.
No, isn't that then IT is 9 divided by 100?
Oh, IT is equal to no, because the 100 ohm resistance will not get the whole 9 volt, because it will be divided between R2 and this branch.
Okay.
This RT will not get full 9 volt.
Okay.
So we have to measure the voltage across the resistance using the meter. We can do also a hand calculation on that, but yeah, we have meters, so we can just measure the voltage across RT using the meter in the simulator. Okay, recording. I mean, there in Spain. Yeah, I'm recording, but this is recording the screen. You wanna go to the camera? Yeah, I mean both camera and this camera is. Okay.
Yeah, I think so.
You want. Yeah, they come back to the. Yeah, I mean, your IC actually. He doesn't split, so it takes a separate path, that goes to reaching those two answers. So it's he's.
Here, IT here.
Yep.
Here's science.
Maybe go back.
And how, one question I was having, which is, in order to mention lost emphasis,
So here, you know, it's the way to find it. Instead of right on the page. Just that should flex.
It's already one, right?
That would. Here, this one, charts of things.
is I would take
Wait,
like IT. And the course. Serious.
I think mine needs to occur. Those things. It's not.
So anyone got the voltage across the resistance? I mean RT. How much is it?
That'd be finished.
Doesn't really matter. You go with it. So let's start this. Let's start this. Just 0.5. This is what that is. This is the negative. This here is usually like we want to measure. Yes. You can find the same voltage will be across both. Now we have this voltage. So this one.
Here.
Yes. Mhm.
VR.
It's all in the
But you know, the resistance on
So
VR.
yeah, so positive turning is to the left. So small.
couple really. These two are very close. I mean, plus the cost.
So
Okay.
let's take the raised to power one
You actually this is this is like the computer's solution, but in real life, you know, this one here can actually measure.
that you have another five cases.
Volts.
This one can
Just switch your raise. Here.
Our resistance values is 100 ohms. This one, okay,
Just place your mouse on.
no, just
Here.
But the
Yeah, it's not exactly that you need it. You need this stuff with a vote. See if that's what so for a vote, we'll have some resistance.
So yeah, if you connect it properly and if you play
Measures voltage.
if you keep the resistance values properly, I mean this first resistance should be 100 ohm. If you click the resistance, the properties box should pop up, and you can change the value there. And again, the middle resistance is 1k and the third resistance is 5k. If you connect this using these resistance values, you should get 963 millivolt. This is M. Remember, I told M. M this lowercase m. This is that means milli.
-3.
Yeah, 10 to the power -3. Okay, so this is let's do the hand calculation again. Maybe. So we have got 963 millivolt. So we need to convert it to volt to properly calculate, maybe in the calculation. So 963 millivolt, if you want to convert this to only volt, we are, I think, yeah, so we are used to see volt, right? Not millivolt. So if we want to convert it to to only volt, then we have to just divide it by 1000. I mean 10 to the 3 or 1000. So that will convert this value to volt. Okay, so that should comes down to 9.963 volt. Okay, so 963 millivolt means 0.963 volt. Okay, so we have got the voltage across the 100 ohm resistance. Then according to Ohm's law, we can calculate the current through this 100 ohm resistance. So which we have named as IT. So IT equal to V divided by R. So V is the voltage across that resistance 100 ohm, which is 0.963 volt, and the resistance value is 100. So if you calculate that, then you will get 0.00963 ampere. The unit of current is ampere. So this much current is flowing through 100 ohm resistance. So this is 0.963 ampere. So this current will come to this point. I mean the total current is 0.00963 ampere. This current will come to this point and it will be divided between these two resistances, right? So in the hand calculation, we can calculate that the I1 is equal to 0.00963 ampere into, when I'm measuring the R1, I mean across, I mean through the resistance 1K, I have to take the opposite resistance, which is 5K here, So I'm measuring the current through this 1K resistance. So I have to take the resistance, the opposite resistance, which is 5K, then I have to add 1K and 5K. Then I should get something. I need to calculate this actually. This is actually a hand calculation, and we will also verify this through our simulation. So in the calculator, I'm putting 0.00963 5 divided by 6. So it should be 0.008025. Very small numbers, right? Ampere. So I should get 0.008025 ampere. And for I2, let's mark this number because we will check this with our simulations. So we should get this current value through the 1K resistance, and for the I2 we should get, we have to calculate like this: the total current 96.00963 into the other resistance is I'm measuring current through 5K, so I need to take 1K in the numerator and the same 1K plus 5K in the denominator. So that should give me 0.001605 ampere. So also keep a note here that theoretically we have got these values, current values through R1 and R2. Now let's measure the current through R1 and R2. Again, suppose we have only voltmeter. So in this case, we have to measure the voltage to measure current I1. I mean, measure current I1, the current through the 1K resistance. We need to connect a voltmeter, right? The positive terminal should be connected to the top terminal, and the negative terminal should be connected to the bottom terminal, because the top terminal is in higher voltage, and this is the ground. This is 0 voltage actually. So we can measure the voltage using the voltmeter, and then again the same Ohm's law. We can find the current from the Ohm's law. That's I1 is equal to the voltage we measure across the 1K resistance, and we know I equal to V divided by R. The resistance is already 1K. So from this we can get the current value through 1K. In a similar fashion, you can also measure the current through 5K. Now, so you have already made the circuit. So I think if you connect the voltmeter, you will get the voltage reading. So get that. Let's see what these values are. So here I am connecting another meter to measure the voltage. Look, we have this meter actually can look in this simulation or simulation tool. The meter can measure current actually. There is a ammeter setting, but we are not using it because to sync with the physical experiments, we are actually not using the ammeter because we do not have the ammeter. So that's why I'm using the voltmeter in the simulation tool as well. So let's connect this voltmeter to the. I told you that I need to connect the voltmeter's positive terminal to the top terminal of the resistance 1, and the negative terminal, I mean the black one, should be connected to the bottom terminal of the resistance 1. Now this voltmeter or meter should measure the voltage across the resistor R1. This is the R1 resistance. So let's start the simulation. So the voltage is 8.02. If we divide this 8.02 by the resistance value, we'll get the current through the resistor. So the resistor value is 1 kilo ohm. So if we divide 8.02 by 1000 or 1 kilo, then we'll get the current. So let's measure that. So voltage is here. We measure that 8.02 volt. And the resistor is 1K. I am writing it as 1000 ohms. So it should be point. If I divide 8.02 by 1000, we will get what? 0.00802, right? Okay, so this is the current using simulation. this is the current value using simulation through R1, right? This is the current using simulation through R1. And what did we get theoretically? We got 0.008025 ampere, and here we are getting 0.00802 ampere. It's close actually, because the simulation also doesn't go too far after the decimal point actually. So that's actually rounded somehow that has been rounded actually. So this is so you can tell these are very close numbers. So yeah, in our hand calculation we got 0.008025, and in our simulation we got 0.00802 ampere. So in the same way, we will connect another voltmeter across this 5K resistor. So this is the voltmeter, and this is the positive terminal of the voltmeter. The positive terminal of the voltmeter should be connected to the top terminal of the resistance, and the bottom terminal of the resistance should be connected to the negative terminal of the voltmeter. And then we will get the voltage across the 5K. Okay, and from the voltage we can calculate the current using Ohm's law. Okay, so let's go back and take another meter and connect the positive terminal to the top terminal of the second resistor, and the negative terminal to the bottom terminal of the second resistor. So the voltmeter is connected. Now let me start the simulation. It should give the same value, because the two resistors, as I have told you, that the two resistors are in parallel. If two devices are connected between the same 2 points in the circuit, all devices actually, those all devices should get the same voltage. Okay, because as you can see, let me go back to the circuit drawing. As you can see here, this 1K and 5K are connected between the same nodes. This is a node actually. This is a node and this is another node. By node you mean a point in the circuit actually. So the 1K and 5K, the top terminals of the 1K and 5K are connected together actually, and the bottom terminal of the 1K and 5K are connected together as well. If these kind of things happen, all the devices will get the same voltage. Okay, but as you can see, that the first resistance 100 ohm does not have the same voltage, because the two terminals of the first resistor is not connected similarly as the last two resistors. As you can see, the left terminal of the first resistance is connected to the voltage source. Yes, but one terminal of the resistance is connected to the other resistances, but the other terminal is not connected to the resistances. So this will get different voltage, but these two will get the 1K and 5K will get the same voltage, because they are connected between the same two terminals. Okay, so that's what is being shown here actually. So the both two resistors will get 8.02 volt. So let's calculate the current. So sorry. So the voltage across the resistor is 8.02. To measure currents using Ohm's law, we have I equal to V divided by R. We got V equal to 8.02 volt, right? And the resistance value is 5K. 5K means 5,000, right? 1K means 1,000, so 5K means 5,000. So if you divide 8.02 by 5,000, let me calculate that. It's 0.001604 ampere. So let's match that with our hand calculation. What was our I2 for the hand calculation? It was 0.00, here as you can see, 0.001605. And here we got 0.00 1604. There is a very little mismatch, but that's not a problem. And these two actually closely matches. So yeah, that's how you will get the current values. And actually here we verify the current divider rule. Okay, so in this, is there any question in the simulation section? I mean, I have done the simulation till now. Do you have any question regarding this current divider rule or the procedure of measuring the current? Anything? Let's see here. So, do you have any question about the current divider rules? Because these rules are very fundamental to electrical engineering. So if you want to do some cheap designs, you have to know these rules. Okay. So if there is no question, so the next part is harder, but yeah, I think it's already 1:55. So you have your kit, right? So you can do that in your home, but because that's not a high voltage, you will not get shock working with this 9 volt. So no worries about that. You can make so what will you do in the hardware? It will do the same thing what I have done in the simulation, right? So you have to just make this circuit. You have 3 resistors. Maybe the resistor values are not like this 1K or 5K. You have different resistors. So you have to make. Let me clearly draw this. So I'm just redrawing this freshly. So you will make the same circuit with the breadboard. You have 9 volt voltage source, but you know that this is not 9 volt. Before making the circuit, please measure the voltage of the voltage source. Because today you are measuring 9.5, but tomorrow it may not be 9.5. It could be something, or it could be 9.5 as well. So whatever before measuring, before making the circuit, please measure the voltage value of the battery and pick any resistance you want from. You have 4 resistors in the bag and maybe. So you have to use any 3. So for RT you can use anything, any resistance. For R1 you can pick any resistance, and for R2 you can pick any resistance and make the circuit. And using the same way, using the Ohm's law, measure current through every resistor. And do some hand calculation as the voltage divider rule, and match them with the hand calculations are in theory, right? So you have to match the theory results. I mean the theory results current values and with your hardware measurement. So the current value I1, I2 should match actually with your hand calculations. So this is your one hardware task, and there is a software task in the slide, which is homework 1. So in the slide you will get homework 1. I think they are self-explanatory. Just explore them. If you so just explore them and see what happens. Actually, in this homework there are different parts. The parts are actually basically the same thing. Just in the different part, we have to use different value of resistance of Rx. Okay, so depending on the value of Rx, the bulb will glow or will glow in the middle range or will not glow at all. So just check this, just explore this. It will be fun. Okay, so just make this circuit in Tinkercad and change the value of Rx according to the instruction written here, and you will see if the bulb glows or not or something. So just explore. This is for your fun, for your enjoyment, and this is one more. This is software. You have to do it in the software. Let me be clear about it. This is homework 1. This one is totally in software. You do not have to do it physically or in hardware. You have to do in hardware this part, which I have shown here. So you have to make this circuit and measure the current. This homework is not properly written in the slide. I will write this homework properly in the slide and update. I will upload the updated version. Okay. So this one would be your hardware experiment, and that one in the slide that will be your software experiment. Okay. So take your time. Yeah.
This one right here, will that be put on the classroom thing? Are you putting it?
Yeah, I have not updated it in the slide.
Oh, okay.
I will make a proper figure and write proper instructions and add it to the slide and upload it. I will upload the updated slide. So in there, the hardware experiment or hardware homework will be assigned properly. So yeah, you have these two homeworks, and take your time if it takes much time. You do not have to submit it next week, but try to submit it. I will not submit it. Actually, you will know that it goes well or not, and let us know that you could do it properly or not in the next week. Yeah, we will answer the questions if you have. And if you face any problem, just let us know. And if you face any problem, you can for a quick check. You can also post in the classroom maybe or in the comment section. I will answer. Yeah, that would be, I think, good. So yeah, that's it for today. We can throw it away. Thank you so much for listening.